Okay, maybe it's a time. So welcome to this morning's session. Our first speaker is Professor Bernardo Cockburn, distinguished McKnight professor at the University of Minnesota, and he's a Frontiers of Science Award winner last year. And he is a pioneer in discontinuous galaxy method for numerical PDEs, and he was an invited speaker of ICM. He will present the transforming civilizations into space today, and please welcome Professor Cockburn.
Thank you very much. Can you hear me? Yes, yes. Okay. So what I want to do today is to show you in a very simple setting how to transform stabilizations into spaces. So what this I mean that usually the numerical schemes have to have some kind of mechanism to render them stable, but these terms are usually thought of just stabilizations. What I'm going to show here is that if we are able to transform these stabilizations into spaces, then these new spaces could improve the accuracy of the solution. So essentially what I'm saying is that stabilizations can give rise to higher accuracy. Okay, any question? Okay, so I'm going to talk about the model problem. Then I'm going to consider two methods. One is the continuous Galerkin method, and the other is the discontinuous Galerkin method. And I'm going to ask why they are not the same. And then I'm going to use some Redal polynomials as tools to establish a link between them. And I'm going to focus my interest in the stabilization term. Then I'm going to show how to transform the stabilization, and then how, this transformation is going to give rise to a local post-processing that I'm going to prove superconvergence. And then I'm going to talk about possibilities of extending this to other PDEs, and I'll give you some references. Okay, so let's begin with the simplest possible PDE, which is an ODE. So U is a scalar function, and F is a nonlinear function of T and U. So this is our model problem, and I'm going to talk about two schemes associated for this method, for this ODE. The one called the continuous Galerkin method was introduced back in 1972 by Bernie Hallman. So he introduced the continuous Galerkin method as follows. So we have an interval in that go from Tn minus 1 to Tn. And in this interval, the continuous Galerkin approximation is taken as the element of polynomials of degree k plus 1, pk plus 1, that solve the following equation. So you have here the ODE. See, this is du dt equal to f of tu, and we multiply this by a test function v, and we take the test function in pk. And then we enforce a continuity at the point Tn minus 1. So how many equations do we have? We have, okay, so this is uk has k plus 2 parameters. Here we have k plus 1 equations because v belongs to pk, and this is the other equation that will determine the solution. So this is, as you can see, this method is continuous, produces a continuous approximation, and is a method that we will call at this point Galerkin, a Petrov-Galerkin method, because the test space is not the same as the trial space. This is pk plus 1, and this is pk. So this is a method that is a Petrov-Galerkin method. Is not the Galerkin method. Okay, so around the same time, in 73, Reed and Hill and also Besson and Ravier in 74 introduced the DG method. Reed and Hill introduced the DG method in a very small technical report, and Lesin and Ravier did a more academic work on the method. In particular, they showed that when applied to this ODE, it reads as follows. So again, on this interval, Tn minus 1 to Tn, this continuous Galerkin approximation is the element of the space of polynomials of degree k, so not pk plus 1 as in the continuous Galerkin, but pk only, that solves this equation. Okay, so some equation here, I'm going to say what is that later, but what I want you to notice is that this is now a Galerkin method. It's not a Petrov-Galerkin method because the space of trial functions is the same as the space of test functions. Now, how do we obtain this equation? What we do is we go to the original equation, multiply by a test function, and integrate by parts here. Okay, so you see we have integrated by parts here, and in the boundary we introduce new variables which we call the u hat. So these are new variables, and u hat is an approximation to the trace at the Tn point, at the intermediate point. And the definition of u hat is the limit from the right, from the left, limit from the left. So here we are saying that the flow of the information goes from the past to the future. So if we want to compute in Tn minus 1 and Tn, we have the ODE here, but we have also some data that come from the previously computed solution. Okay? Any question? Okay, so now let's make a little digression here. So I'm going to establish a bridge between the CG method and the DG method. And in order to do that, we need some special functions R n k plus 1, which have the following properties. It's a polynomial of degree k plus 1, is 0 at Tn, and is 1 at Tn minus 1, and is orthogonal to pk minus 1. Now, these conditions look funny, but the analysis is going to tell that these conditions have to be satisfied. I'm going to show you when we do this. So for the moment, let's assume that we have some R's like that. Okay, so now I am going to start to rewrite. What I'm going to do is I am going to grab this weak formulation and I am going to write it like this. And then you can see that in order to do that, I have to integrate by parts. So I integrate by parts here, and I put a udg, and I'll have an extra term. This extra term has this form: u hat dg minus udg times v evaluated at Tn minus the evaluation at Tn minus 1. Okay. And if you remember, this is called the upwinding trace. This is upwinding because we take the value from the past. We take the value from the past. So this u hat is equal to u minus is minus here. Okay. So you had minus ud is equal to 0 at Tn because of that, and it is different from 0 at Tn minus 1. So I only write that this thing is equal to this minus that. And this term, I'm not going to show you this here, but this term is responsible for the stability of the method. So I have to do some complicated computations to show you that, but here we have the information that we are taking the information that comes from the past, not from the future, and so this makes the method stable. If we were taking the information that comes from the future, of course this doesn't make any physical meaning and the scheme would be unstable. But since we are taking the information that coming from the past, the scheme will be stable. So this is called the stabilization term, and this is what I have to focus my efforts. Okay. Any question? No questions? Yeah.
In many questions, so for the PG method, usually the stabilization you should have the scaling with respect to the mesh size. So in this case, your ion is
There is no in the original DG. You just take the previous guy. That's it. So there is no H. So you see that essentially you have some kind of this is UDG plus, and this is UDG minus. So it's the jump. So the stabilization in this case depends on the jump, only on the jump. There is no H or anything like that. Though those things become natural for elliptic equations, but not for this thing, and on other cases, yeah. So the original method doesn't need that. Yeah, of course you can modify the original method and put some constant there. We don't want to do that. Okay. Okay. Any other question? Okay. In any case, we could explore the possibilities of what happens if you do that, but let's begin with this one. So, all right. Okay. So now, what I'm going to do is I'm going to work very hard on the stabilization term. And what I want to do is to transform this guy in something like that, v times the derivative of something else. Okay? All right. So here we go. So in the first line, I just repeated what the stabilization term is. So we have this jump across the element, and I'm going to leave this untouched. So this guy is going to be untouched, and I'm going to work on this thing. So I write this. This is very, very simple, as you can see. This is equal to 0 times that minus 1 times that. Then I take a function r, which is 0 at Tn and 1 at Tn minus 1. So this is this property and this property. So these two properties come out because I want this to be like that. Now, why do I want to be like that? I want this to be like that because then I apply the divergence theorem, so to speak, right? And then I have that this is equal to the integral of the time derivative of this times that. And now I differentiate this product, and I will have this term only if this times pk minus 1 is 0. You see that here v is a test function, we live in pk, but the derivative lives in pk minus 1. So if I request that Rn be orthogonal to pk minus 1, I can write that. And then you see that I already have what I wanted. I have the stabilization term is a constant, which I can put inside here, times v times the time derivative. So I can now do this is the more difficult part of the work. So I can put here this jump and the polynomial here, and so this I call the post-processing DG, or the new approximate solution. It is equal to the old approximate solution plus this term, and this term comes from the stabilization. So in this way, I have transformed the stabilization into space spanned by this function. Okay, and then what happens with this DG? Well, this DG is pk minus 1, is pk plus 1, this guy is pk plus 1. It is equal to, is continuous, because at Tn minus 1, this is 1, and then this cancels that, and HDG is equal to U hat, a single value. So it was discontinuous, but now it's continuous. And then this DG, the value of this guy is equal to the value of this guy on all the zeros of R. Right? If the R is 0, these two things are the same. Okay. So the theorem is that the DG method can be written this way. This is DG, but this is DG star. And we have seen that we rewrote the stabilization term as the integral of V, the time derivative of the jump times R. And so we have added this term there, and the weak solution is this one. And this DG star is continuous, as we saw, and so this is the rewriting of the original formulation of the DG method. Any question? Okay, so let me compare this with the CG. So this is the DG and this is the CG. So the only difference is who sits here. For the DG method, this part is exactly the same. Exactly the same. And for the only difference goes into the right-hand side, not in the discretization of the derivative. So the discretization of the derivative is exactly the same, but the right-hand side is different. This is pk plus 1, but this is pk, right? Now, we have a corollary, and the corollary is the following. So suppose that we approximate this function by a Lagrange interpolant at the zeros of this polynomial. Then, as we have seen, this is equal to that. So the DG star is equal to the U hat, and then when we interpolate these things, we get here a new method that is the CG interpolant of F, and this method is called the discrete Galerkin. Bernie Holmes proved that the discrete Galerkin converges with order k plus 2 in L infinity, and so we have that this guy is equal to this guy, this converges with k plus 2, and this means that this value itself superconverges with order k plus 2 at the k plus 1 zeros of R. Okay, so this guy originally can be proven to be convergent of order with order k plus 1, But since we have this particular equality and this method converges with order k plus 2, we have that this converges at order k plus 2 at the k plus 1 zeros of R. So the results then essentially say that stabilizations, if transformed suitably, can generate better approximations. Here we have that at some point we have at some point this guy superconverges, but also this guy converges uniformly in L infinity with k plus 2. UDG converges with order k plus 1, but UDG star converges with order k plus 2. And in order to obtain the convergence, to enhance the convergence, we have to add this term. So this guy converges with order k plus 1, you add this little term, and it converges with order k plus 2. So that's the message. The message is that stabilizations can be transformed into something, into spaces which can enhance the accuracy. Okay. And that. So I think I'm going to finish before time. So the question is, can this be done for any PDE in a systematic manner? Can additional orders of accuracy can be gained? And so we are working on this with a bunch of collaborators. So with Zubin Lal, we are working on discontinuous galerkin for CFD. With Srivatsa and Tharamu, we are working for we are applying this to the continuous galerkin method for PDEs. And then we are working with Green and Pereire, also for CFD, with Juwan of University of South Carolina, not North Carolina, South Carolina. Superconvergence of functionals with Shukaidu and Sanchez on shallow water and KDV equations, with Alexander Ern Friedrich systems, and with Oikawa in Japan with mixed methods of diffusion. And so let me show you the work that we have done very quickly with Zubin Lal. So we have UT plus UX, and UT, we assume that we apply the technique to this term, so in X, not in time, and this is the result. So you can see, suppose that we have a sinus, oh, sorry about that. We have a sinus that is moving with periodic boundary conditions, and then after a while, you see the dashed line, that exact solution. And we are using P1 elements. Here we have 10 elements, and you can see the P1 approximation here, the P1 approximation there, the P1 approximation there. And then to this point, to this continuous galerkin method, we add this term. So it has the same form that we add this term. Some jump times spatial function. That can be written very, very easily in terms of Legendre polynomials. And so this polynomial has a 0 here and a 0 there, and it's 1 here. So that's why when multiplied by the jump, it gives a continuous approximation. So the black line represents the post-process solution. So this piecewise linear guy converges with order 2, and the black guy converges with order 3. We have a proof of that. And the unique thing about this approach is that it works for it can give you a superconvergent on non-uniform meshes. So far, the only proven solutions for post-processing non-uniform meshes are for very smoothly varying smooth meshes, not for arbitrary ones. So here we have arbitrary meshes with 8, 9, 10, 11, and so on elements, and you can see that we have here the comparison between the uniform mesh in a in a dark line. This is the uniform mesh, and this is the post process. So this is P1, k equal to 1, and here we have order 2, here we have order 3. So you see here, this is 10 to the 0, this is 10 to the minus 3, this is 10 to the 0, 10 to the minus 3. Then we go to 2, and we get some kind of funny stuff about the non-uniformity of the meshes. You can see that here we go from something 10 to the minus 2 to something 10 to the minus 4, and here we have 10 to the minus 3 to 10 to the minus 6. So this is because this goes for order 3, this is order 5. And finally, if we count order 3, we get order 4 and order 7. And so that's that. So the references are, these are the two papers by Bernie Haumer about the continuous Galerki method and the discrete continuous Galerki method. And this is the paper by Rita Hill, and this is the paper by Lesan Rovier. So these are background papers. And let's see what else. These are our work, and this is what this is the paper that has the computation in which we transform the stabilization into spaces. It has appeared in this new journal, the Beijing Journal of Pure and Applied Mathematics, right? That is from here. And what I like about this paper is that it only has 7 pages, because he only have that that computation. And if you want the results about the transport equation, you can see that there in JSC. That's it.
So, is there any question from the audience? So maybe I have a couple of questions. So have you tried this idea with this post processing? I mean, with this UDG star for more complicated problems? Because in my mind, I think the original maybe maybe more like a later days than the 70s, but definitely earlier than now. I think the motivations for developing DGs to capture some discontinuous phenomena in hyperbolic equations like the shocks, and also for the work that I've done, I found the DG is better than the continuous DG because it can be more flexible for this this plate deformation problems in elasticity. So
Yeah.
my question is, have you tried this idea for more complicated problems, or do you think if this new method can still have these advantages of this DG for these problems?
Yeah, that's a good question. So this post-processing doesn't change the method. It's the same method, but we can extract more accuracy than we thought possible. So, for example, for the work we have done for this work, we apply the post-processing only once at the very end of the simulation. And then we can extract not k plus 1, but 2k plus 1. So if you have a shock, So it's the same method. And the method helps you if you have a region in which the solution is smooth. So instead of k plus 1, 2k plus 1. If you have a discontinuity, this post-processing doesn't give you anything better. Is that what you ask?
Yes. Basically, that's what I want to.
And then what happens is that essentially you are going backwards. You are going against the idea of DG, right? Because you're making this continuous, and so for example, the post processing for Q1 is, let me see, the post processing for Q1 is continuous. The post processing for K2 is C2, and the post processing for K3 is C3. So you are going against the idea of CG, right? So to do that for all the PDEs, it has to do with how do you deal with the corresponding term. And the difficulty is to come up with the transformation of the spaces that take into account not only PDE but also the geometry of the elements. So this is what is difficult.
I see. Thank you. So maybe I have another question. So I think now you get the super convergence, and I think that's not for free. And so my question is, so how about the computational cost of this post-processing step?
Yes.
So,
yes. I mean, you can see here, right? In order to compute the post-processing here, you only have to. So you have this guy, and you have to add one element, right? You have to add one of these guys. In order to compute this, you only need to take into account what's the jump, and you multiply this by a fixed function. So here you see you compute this. If you want to do the post processing here, you compute one guy and multiply by a special function, and you add it. So it's super fast.
I see.
Now, suppose that you are doing this is for k equal to 1. Suppose that you have to do k equal to 2. You have to do this twice iteratively. So if you have k, you have to go all the way to p2k, and then you have to do k iterations of the same type.
Okay, I see.
So it's very local. It's very local. You can do it recursively.
Yeah, but okay, I see. But you need to do it on all the elements, right?
You have to do it. You can do it in parallel on all the elements.
Okay, I see.
Yeah.
So I saw this post-processing was originally illustrated for time discretization, and you also have this for space discretization, and also triangular mesh.
This is okay. So here, for example, to do this case, we assume that in order to devise the post-processing, we assume that we don't discretize in time.
No.
So all the post-processing is done in space. We have not done post-processing in time.
But you illustrated this for time discretization of ODE before.
Yeah, you apply this post-processing in space once at the end of the simulation.
Okay. And also, can it be nonlinear f of u in the space derivative, inside the space derivative? For smooth, let's say solution is smooth.
Yeah, for smooth solutions it's fine. For the other solutions, we don't know.
So for smooth solution, you can solve the hyperbolic conservation law, right?
I mean, for suppose that this is the linear case, right?
Yeah.
And you have a discontinuity. This post-processing doesn't improve the approximation. Mm-hmm. Give you essentially the same.
Yeah. Let's say for nonlinear.
For nonlinear, we are beginning to do that.
Okay.
We believe that we are not going to see any improvement either. Because for linear, we don't see any improvement.
But for nonlinear, I mean, if the solution is smooth.
Oh, yeah, yeah. For the solution, if the solution is smooth, you do see 2k plus 1.
Okay.
Yeah. Yes. But we don't have a proof yet. So we have a,
Well, what about for triangular mesh?
well, we don't know. The formulas get very complicated very fast. So we are trying to simplify them, and so far we don't have anything. So you see, this is a very recent work. This is 2025. So this year, and then this is based on, yeah. So it's very.
Okay, thank you.
This just came out of the oven. Very simple. We have a
So
question there.
You mentioned sometimes you use a non-uniform mesh.
Yes.
So is there any systematic way to how to find the like
How to find what?
the mesh, like how to design the mesh for your problem?
Oh, so you mean adaptivity? Adaptive meshes?
Yes.
Yeah, we were not interested in doing adaptivity at this point. We are going to try. But at this point, what we did, the meshes, the non-uniform meshes we have are constructed as follows. You take the interval and you distribute, you chop uniformly, and then you move the point to the right to the left in such a way that you don't collapse two guys.
Okay.
So and we do that randomly. So this means that whatever crazy mesh we have, we can deal with that. So the next step would be what you want to do. To do how to devise the adaptive mesh based on this stuff. Yes, we have not done that.
Okay. Thank you.
Yeah.
is there any other question from the audience? Okay, so if there's no other question, let's thank our speaker again.
Yeah. Let me answer a little bit more to. Sorry. I have time, right? Have time? Plenty of time. Plenty of time. Yeah, you can see that we have the approximate solution, the DG approximation, and the post-processing. So you know that the DG approximation is order k plus 1, and the post-processing is order 2k plus 1. So the difference gives you an estimate of the error. And you can use that to construct the mesh, to do adaptivity. Yeah. Okay.
So let's thank our speaker again.